Hello everyone, I welcome you all to my channel. In this video, we are going to discuss important topic from Unit 5, that is Design for Testability and Boundary Scan. So first let us see what is the necessity for testing. So if we go for real estate means, there everyone will say the word location, location, location. So similarly in IC design, we use the word testing, testing, testing because testing is very important in IC design. So here there are three main categories. First one is functionality test or logic verification. Second one is silicon debug and third one is manufacturing test. So due to the dust particles or missing contacts, there may occur fault. So we have to check these faults using the testing methods. So first let us see the contents in detail. Design for testability. Under this topic we are going to see ad hoc testing, scan design, built-in self-test, IDDQ testing, design for manufacturability. And the next topic is boundary scan design. So first let us see design for testability. So design for testability, from the word itself we can understand testability. So if we consider a circuit to be testable means then it should have controllability and observability. So controllability means it is the ability to set the value or reset the value at any node in the internal circuit. That is, for example, if you are going to test a circuit means inside that there will be several number of nodes. So at each node we have the capability to set or reset the value. Then it is called as controllability. The second one is observability. So observability is the ability to observe either directly or indirectly the state of any node in the circuit. So this is used for checking the output. So controllability means giving the input value either 1 or 0. Similarly, we can check the output using the observability. So first let us see ad hoc testing. So ad hoc, from the name itself we can understand it is a collection of ideas. It is used for reducing the combinational explosion of testing. So this type of testing is used for simple circuits or simple designs where scan, ATPG, these are testing methods. Built-in self-test are not available. If these tests are not available means then we can use this ad hoc testing. So the following are the common techniques for ad hoc testing. First one is partitioning large sequential circuits. Second one is adding test points. Third one is adding multiplexers. And fourth one is providing for easy state reset. So partitioning large sequential circuits. So large sequential circuits can be partitioned and then testing is performed. Then adding test points. If you are having a very complex circuit, we can add test points at several places in order to find out the result. Then adding multiplexers. Similarly, providing for easy state reset. If you want to give a reset value, that also easily we can give. So the technique classified in this category is the use of bus in a bus-oriented system for test purposes. So the bus used in bus-oriented system is used for loadable, that is data can be loaded into the circuit. Similarly, the data can be driven from the circuit to the bus. So using that also we can test the circuit. Normally, multiplexers can be used to provide alternative signal path during the testing. So in general, this ad hoc testing represents a bag of tricks developed over the years by the designers to avoid the overhead of systematic approach to testing. So this ad hoc testing is not a systematic approach. If we go for systematic approach, then definitely the complexity will increase. But in this ad hoc testing is used for only simple designs. There is also a drawback in this ad hoc testing. So the drawback is here the chip complexity is more. So to overcome this chip complexity, we go for structured approach to testing. So the next one is scan design. There are two types. One is serial scan and another one is parallel scan. So this scan design strategy for testing is used for providing observability and controllability at each register. That means for each register, if we provide observability and controllability means, then definitely the testing process will be very easy. So in this design, the registers operate in two modes. One is normal mode and another one is scan mode. So in normal mode, the operation is in normal fashion only. There is no change, normal operation. In scan mode, what happens means here a giant shift register called scan chain shift register is formed by connecting all the registers together. Okay. Then by applying n clock pulses, the n bits of the state in the system can be shifted out and n bits of the state can be shifted in. That means if you are applying 4 clock pulse means then 4-bit data will be shifted in, and if we apply 4 clock pulse means then the 4-bit data will be shifted out. So this made easier for observability and controllability at each register. So modern scan is based on the use of scan registers. So the scan register is nothing but it consists of a D flip-flop preceded by a multiplexer. That means a multiplexer followed by a D flip-flop. So when the scan signal is deserted, that means if the scan signal is equal to 0, then the register behaves as a conventional register. That means it is in normal mode, storing the data on the D input. When the scan is asserted, that means when the scan value is equal to 1, the data is loaded from the SI pin, which is connected in shift register fashion to the previous register Q output in the scan chain. So this can be easily understood. By seeing this figure, this is the architecture of scan-based testing. So here, this is the scan register, D flip-flop preceded by a multiplexer. So here everything is connected in a serial fashion. That is, first flip-flop output is connected as input to the next. Then the second one output is connected as input to the next. Like that, it is connected in a serial fashion. Then finally, you will be getting the scan out. So in this scheme, every input to the combination block can be controlled and every output can be observed. So this is the main advantage of this scan-based design. Here also, the test generation for this type of architecture can be highly automated. That means automatic test pattern generator techniques can be used for combination blocks, and as mentioned, the scan chain is easily tested. Then there is a drawback. The drawback is area and delay impact of extra multiplexer in the scan register. That is, area and delay will be more. So here the figure shows the parallel scan basic structure. So here the scanning process is done in a parallel manner. So the next method is built-in self-test. So from the name itself we can understand built-in self-test. So to test the circuit automatically there will be a built-in self-test structure inside the IC. So this is used for testing the IC. So self-test and built-in test techniques, as their name suggests, rely on augmenting the circuits to allow them to perform operations upon themselves that prove the correct operation. So these techniques add area to the chip for the test logic, because this is an extra circuit that is added to the IC for testing purpose. So area will be more. So the methods for testing the module is signature analysis and cyclic redundancy checking. So first we are going to use the cyclic redundancy checking. That is, this involves a pseudo-random sequence generator to produce the input signals for the section of a combinational circuitry and a signature analyzer to observe the output signals. So PRSG is used for giving the input signals to the circuit which we need to test, and to verify the output or to observe the output we use the signature analyzer. So this PRSG, that is pseudo-random sequence generator of length n, is constructed from a linear feedback shift register, that is LFSR, which in turn is made up of n flip-flops connected in a serial fashion. So this LFSR consists of n flip-flops and also it is connected in a serial fashion. The XOR of a particular outputs are fed back to the input of the LFSR. An n-bit LFSR with cycle through 2 power n-1 states before repeating this sequence. So they are described by the characteristic polynomial indicating which bits are fed back. A complete feedback shift register is shown below. Pseudo-random sequence generator is used for giving the input signals, and to analyze the output we use the signature analyzer. So the signature analyzer receives the successive outputs of the combination logic block and produces a syndrome that is a function of these outputs. So by verifying this syndrome we can say whether it is correct or wrong. So normally this syndrome is compared with the correct syndrome. So correct syndrome is derived by running the test program on a good logic. So if you are having a test program means then we have to verify it in a correct circuit and we have to get the output. Then we have to compare whether that output and our output is equal or not. So from this itself we can check whether it is a defective circuit or it is a correct circuit. So this is the structure for pseudo random sequence generator, which is constructed using LFSR. Pseudo random sequence generator is used for giving the input signals, and to analyze the output we use the signature analyzer. So the signature analyzer receives the successive outputs of the combination logic block and produces a syndrome that is a function of these outputs. So by verifying this syndrome we can say whether it is correct or wrong. So normally this syndrome is compared with the correct syndrome. So correct syndrome is derived by running the test program on a good logic. So if you are having a test program means then we have to verify it in a correct circuit and we have to get the output. Then we have to compare whether that output and our output is equal or not. So from this itself we can check whether it is a defective circuit or it is a correct circuit. The next method is IDDQ testing. So this method is used for testing the bridging faults. So first we have to understand what is bridging faults. If you are having two signals and that two signals should not get shorted or connected together, but in some cases it may get shorted or connected together. So that type of fault is called as bridging fault. So this fault can be identified using IDDQ testing. So it is VDD supply current quiescent, that is due to the leakage. By verifying the leakage current value, we can test the circuit. So when a CMOS logic circuit is not switching, that means there should not be any DC current flow. But due to some input combination, there will be some DC current flow, that is the leakage current. So by measuring that leakage current, we can say whether the circuit is a correct one or a defective one. So this is called as IDDQ testing. The next one is design for testability. So the circuits can be optimized for manufacturability to increase their yield. So this can be done in different ways. The first one is physical. So at physical level, the yield can be increased by improving or reducing the effect of process defects, that is increasing the spacing between the wires where possible. If you are increasing the spacing between the wires, then definitely the short circuit problem can be avoided. Similarly, increasing the overlap of layers around the contacts and wires. So this is the chance of misalignment. Then next one is by increasing the number of wires, that is contact at wire intersection. So by increasing this, there is a chance to reduce the defect causing due to open circuit. Then the next thing is redundancy. So we can add the redundant structures which can be compensate for defective components on the chip. So if any one of the row or column is defected, means then we can take that redundant structure. So this will help to easily avoid the errors. Then the third one is power. So elevated power can cause failure due to the excess current in wires, which in turn can cause metal migration failures. So this also can be avoided by reducing the power. Then process spread. So we have seen that process simulation can be carried out at different process corners. So this also increases our yield. Then the last one is yield analysis. So when a chip has poor yield, means then we have to take it to the library and we have to perform the yield analysis and find out the root cause of the failure. So these gets improved. So design for manufacturability. Then the next method is boundary scan. So many system defects occur at the board level, including open or short circuited printed circuit board, traces and incomplete solder joints. So if error occur at the IC or chip, means then we have to remove that chip and we are testing it in the bed of nail testers. So this is the normal procedure done. But nowadays the ICs are it is surface mounted ICs, so we cannot remove it from the chassis. So for that purpose we go for this boundary scan of testing chips at the board level. So here the figure shows the boundary scan architecture. So this is IEEE 1149 boundary scan architecture. Here all the input-output pins of each IC on the board are connected serially in a standardized scan chain accessed through test access port, that is TAP, that is called as test access port. And so that every pin can be observed and controlled remotely through the scan chain. So no need to remove the IC from the board. In the board level itself we can test using this boundary scan architecture. So at the board level, ICs obeying the standard can be connected in series to form a scan chain, and the connections between the ICs are tested by scanning the values into the outputs of each chip and checking that those values are received at the inputs of the chips they drive. So by checking these values, we can say whether it is in good condition or in a faulty condition. I hope you all have understood the concepts behind design for testability as well as boundary scan. If you like this video, kindly subscribe my channel and share with your friends. Thank you.